Hey, welcome! I'm Diabeticus and this is part 3. Last video, we got ourselves a general equation that makes a normal line out of a point on x cubed. And said equation is y minus apple cubed equals negative 1 over 3 apple squared times x minus apple, which is quite pretty if you ask me. Anyways, throughout this video, we'll be locating points created by the intersection of two normal lines, and like before, generalizing the process of finding any of that point. Without further ado, let's begin. So in the previous videos, I've talked about how the intersection of two closed normal lines create a point on a cone surface. And since we now have a general equation for a normal line, we can find that point using some simple algebra. To start, let's graph a normal line located at x equals 1 and a closed value x equals 1.1 and find their intersection points. Using our apple equation, we have for x equals 1, y minus 1 equals negative 1/3 times x minus 1. And for x equals 1.1, we have y minus 1.1 cubed equals negative 1 over 3 times 1.1 squared times x minus 1.1. Next, we find the intersection of these two normal lines with a system of equations. And for now, solve for x. And prepare yourself for some massive algebra. Well, actually, you can pause here and solve for x yourself. Or keep playing and I'll go through this equation. And for the sake of saving time, I'm not going to say every number or letter while solving the equation. So pause if you care about reading every bit of algebra that I'm writing down. First off, let's transfer the constants on the y side of each equation to the right, where we have y's only for the left. Because of this, we can equalize the right side of each equation and solve for x. Next, we expand the factors from each side, and then put the x term of the right to the left. After that, put every constant on the left to the right. Following that, we have an x on the left side and then divide both sides with a bigger factor. So we now have x only on the left. At this point, we could just use a calculator and evaluate numbers or simplify the constants further, but I'll take the easy route. What I get from x is negative 5.2, and negative 5.2 is the x solution for the two normal lines. But since we have both x and y on the system of equations, our answer must be of the form xy. In short, we need to find y. To solve for y is simple. We can choose either normal line equation and plug negative 5.2 to x and solve for y. And of course, we'll choose the easier one. Y minus 1 equals negative 1/3 times x minus 1. So now we have y minus 1 equals negative 1/3 times negative 5.2 minus 1. Next, we put the left one to the right and get y. Skipping some steps, we end up with y equals 3.1. Overall, we have negative 5.2, 3.1. So, if we plot negative 5.2, negative 3.1, we can see that the point lies close to a cone surface from the normal map. Now you may already get the point, no pun intended, and move on to generalizing already, because I've done an example. But I also need to address the question, why do we need two closed normal lines in finding the intersection? And because of that, let's take another example, x equals negative 2 and x equals negative 2.5. Okay, let's briefly solve the respective normal line equations. So we have y minus negative 2 cubed equals negative 1 over 3 times negative 2 squared times x plus 2. And y minus negative 2.5 cubed equals negative 1 over 3 times negative 2.5 squared times x plus 2.5. Alright, putting the left-right constants to the right, we equalize and then solve for x. So, number 1, distribute the factors. Number 2, transfer the x's. Number 3, move left-right constants to the right. Number 4, factor the x's. 5, divide by factor. Then, to solve for x, we use the mighty calculator. This becomes 253.06. Next, we solve for y. let's choose the 2 equation and plug 253.06. We have y plus 8 equals 1/12 times 253.06 plus 2. Evaluating the entire thing, we get negative 29.26. All in all, we have 253.06, negative 29.26. Okay, so now if you plot this point, you may notice that it is not quite closer to the cone than the previous example. This implies that the closer the normal lines are to each other, the closer the intersection point will be to the cones. And I want you to hold on to this idea for a moment. Alright, we've tackled a couple examples, so let's generalize. Okay, let's say we have a normal line at x equals apple, which makes y minus apple cubed equals negative 1 over 3 apple squared times x minus apple. And then another one, say at x equals pear, making y minus pear cubed equals negative 1 over 3 pear squared times x minus pear. Oh man. Now let's put the constants to the right, the ones with a cubed on it. Then equalize them, then solve for x. Let's review the steps. 1. Distribute the factors and simplify them if necessary. 2. Transfer the x's. 3. On the left, move everything but the x's to the right. 4. Factor the x's. 5. Divide by the factor. Now, since we only have variables, a calculator will be rendered useless, so we simplify the right side. To do that, let's cross-multiply the denominator, giving us a fraction. Next, we multiply the denominator of the denominator to both poles of the fraction, getting rid of the lowest denominator. Then, factor everything in the numerator and do some cancelling and powering. Lastly, divide everything by 3. And now you have this longest equation for x. Okay, cool. Now we choose either equation and just yeet this entire load and substitute to x to that equation, right? Now we solve for y. It's very, very easy. Sorry. I lost control for a bit. Okay, for now, I'll just present to you my solution for y. But there'll be a reason for me skipping the solving part. So let's pretend for now we spent 20 minutes to evaluate for a while, right? So since we now have expressions for both x and y, we can write a dump truck coordinate with all these fruits on the screen. So what do they mean? Well, these coordinates pinpoint where two normal lines from x equals apple and x equals pear intersect. And because we now have this thing, we're done, right? No, we're not. Remember that we need close values of each normal line for the intersection point to land close to the cone. In fact, the closer both lines get, the more accurate we get to touching the cones. So we need one of the variables, say pear, to approach the value of apple. And oh boy, didn't I just say approach because it's calculus time. This is the part where I use the concept of limits to have pear approach the value of apple, but not really equal to apple, just approach. This is how I would explain it. Say apple's value is 69, funny right? And we want pear to approach apple's value by setting pear to a number close to 69, like 69.1, 69.01, or 69.000420. By taking the limit, we're stacking more decimal zeros to 69, but not equal 69. Anyways, by taking pear's limit, we can change the x equation and the y equation, which has pears and apples, to only have apples, because pear technically becomes apple plus some super small number as it approaches the value of apple. So before we evaluate the limit, let's examine what would happen if pear approaches apple. If pear approaches apple, the pear normal line will tend to become collinear with the apple normal line, as well as tend to become parallel, but not exactly parallel and collinear. just a micro, nano, femto, yocto unit away, and super little slanted compared to Apple line. Because the normal lines are technically still not parallel, they still should intersect at a point. And the closer each line is, the closer the intersection point lies on the cone. So by taking the limit of pair as it approaches Apple to the two jumbo equations, the point will lie quite exactly on the cones. So let's start with the x equation and take the limit as pair approaches Apple. I want you to take a look at this mess. If we plug pair to Apple immediately, then the denominator will equal 0 and ruin the entire equation. So we'll have to make our way around this. To do that, let's separate the denominator into the difference of squares identity. Apple plus pair, Apple minus pair. After that, we do the next step, which is the most unintuitive. Insert these four very long terms with weird powers that overall subtract to 0. The reason for this is to have a polynomial that is factorable to Apple minus pair, which in result turns to this. Check it out. Since we now have an Apple minus pair on the top, those factors cancel out, leaving an Apple plus pair on the denominator. In which case, we can now turn every pair to an apple without breaking the numerical fabric of the universe. Evaluate the entire equation, the terms with the 3 combine, which further simplifies to 1/2 apple minus 9/2 apple to the 5th. If you did not follow through all of that algebra, that's okay, because just knowing that I took the limit of the initial expression is an assurance and proof that this result did not come out of thin air. Anyways, this equation, my folks, is the x value of the intersection of only one normal line, which sounds weird because our friendship with pair has ended once we evaluated the limit as pair becomes apple. In other words, if we set apple to 1, we'll get 4, where if we use the old equation and set apple to 1 and pair to 1.1, we'll get negative 5.2. And if things do not make sense yet, watch as I stack more zeros to pair, making it approach 1. Well, it approaches 4. Therefore, this simple apple-only equation must work like the complicated apple pair one. Now, there's one thing left which I dismissed earlier, the y equation. Because we now have a simpler x equation, we can now plug x to this binomial beauty and solve for y. First, combine the like terms inside the factor. Then factor the negative 1 over 3 apple squared. Once again, combine like terms and boom. We now have 5/2 apple cubed plus 1 over 6 apple, which is another binomial beauty. And good thing November is over. I mean, now we have two equations that yield the x and y of the intersection point of one normal line. And again, pair line gone, only apple line is friend. Alright, remember that the POI touches a cone when pair is close to apple. Well, pair is technically apple now, which means our POI is actually on the cone surface. Moreover, since we have a general equation, or more appropriately, a parameter, which is a coordinate and equation bred together, guess what happens if I plot this parameter on top of the normal map? So drumroll. That's right, we've made the cones ourselves. Can't you believe it? Since any apple on the parameter gives us a point on the cones, well actually a point off the cones, plotting all the values of apple created the cones entirely, which is phenomenal. Since we now have an actual graph of the cones, I guess we don't need the normal map anymore. Goodbye normal map, you were a good friend in all these 3 episodes. But now I have a new friend. Dang, I guess I ended 2 friendships this episode. I'm a monster. Anyways, since we now have a mathematical parameter for the cone, we now have even more information for us to locate the pseudo-focus. which we'll be doing next episode. See ya, gamers. Bye bye.